everybody. Today we will discuss the next chiral auxiliary, that is the aza-enilate and imines and sulfoxides, chiral sulfoxides and hydrosones acts the chiral auxiliary. And we have already discussed the definition of the chiral auxiliary, that is an optically pure compound which is connected to the starting material and do the asymmetric synthesis, and after that we will remove the chiral auxiliary, and that is the role of the chiral auxiliary. So in the last class we have discussed the alkylation of the ester. Today we will discuss the aza-enilate and imine. So first of all, we will discuss what you mean by the aza-enolates and imines. So aza-enilate and imines are produced by when an ketone or an aldehyde react with primary amine, naturally the condensation reaction will occur and to form the imines. So this is the structure of the imine here. So in the imine, the carbon is doubly bonded to the nitrogen, and after the imine formation and the reactant base, due to the base treatment, one of the hydrogen which is near to, I have shown by the that hydrogen, and I have shown by the yellow color arrow. So the hydrogen is pick out by the base as H plus. So there is a negative charge is formed, and that negative charge is shifted here. So that form a C double bond C bond, and the C double bond N, the pi electrons in the C double bond and pi electron in between the carbon and nitrogen is located in the nitrogen. So this is the structure of the aza-enilate. So the imines and aza-enilate is generated due to the reaction of the aldehyde with the primary amine. First of all, it will form the imine and it is converted into the aza-enilate due to the base treatment. So I hope that you understood the formation of the aza-enilate and imine. Now we are moving into the alpha alkylation of the aza-enilate. So you know that the aza-enilate is formed due to the reaction between the aldehyde and primary amine, and after that it forms imines, and imines during the base treatment it will produce the aza-enilate. Here this is the aza-enilate, structure of the aza-enilate. The aza-enilate, the basic we have to concentrate on which bond. So C double bond C, which is singly bonded to the nitrogen. That bond is the specification of the aza-enilate. And during the alkylation, we are adding the alkylating agent as the benzyl chloride, PH CH2Cl, benzyl chloride as the alkylating agent. So naturally the pH CH2 minus will attack on this carbon, and the nitrogen is converted into imines. Again the structure is the alkyl group is added in this carbon atom, and here we can see that the pH CH2 is added, that is the alkyl group which is clearly added to the carbon atom, and again aza-enilate is converted into imine. And after that, after the asymmetric synthesis, we have to remove the aza-enilate, because aza-enilate, the chiral auxiliary, aza-enilate as the chiral auxiliary, and we have to remove the aza-enilate, and carbonyl group is regenerated. The next example, the reaction of the aldehyde with an amine, primary amine. So NBuCH2CHO react with NH2 cyclic ring. So there is naturally there is a condensation reaction will occur and to form an imine. And if you are adding a base like R2NLi. It will eliminate one H plus ions, and negative charge is shifted in between the carbon, and the pi electron is located towards the nitrogen, and that pi electron is form a bond with the lithium. And now we are alkylating the aza-enilate by using BrCH2. This is the fragment. So this fragment is added in the carbon atom. Okay, this is the reaction. After the asymmetric synthesis, asymmetric alkylation of the aza-enilate, we are removing that bulky compound. So the carbonyl group is regenerated. So we have to keep in mind that the imine first of all converted into aza-enilate, then alkylation will occur. So for the alkylation of the imine, first of all we have to convert into aza-enilate, then do the alkylation, then remove the aza-enilate. And for the alkylation of the aza-enilate, first of all we have to convert the aldehyde or keto group into imine, then convert into aza-enilate, then react with the alkyl compound. Then after the alkylation, asymmetric alkylation, we have to remove the chiral auxiliary. Okay, hope you understood the concept. Next chiral auxiliary is the hydrosome. So this is the structure of the hydrosone. I have shown here. This is the structure of the hydrosone. C doubly bonded to nitrogen, which is single bonded to NH2. This is the structure of the hydrosone. So the reaction which I have shown in the bottom of the slide is the preparation of the hydrosone. So first of all, carbonyl group, either it may be aldehyde or ketone, react with hydrazine. So this type of the reaction will occur and to form the hydrosone. So our topic is the alkylation of the hydrosone. Here also hydrosone is he act as a chiral auxiliary. So there are the carbonyl group is the starting material, and we can as SAMP hydrosone. This is an hydrosone. It is react with the carbonyl compound and to form this compound. Okay. Now the carbonyl group can be reacted with the RAMP. So the difference between SAMP and RAMP is the position of the three-dimensional arrangement of the OMe group. So in the SAMP, the OMe is in the upward direction, so towards the observer. In the RAMP, the OMe is away from the observer. That is the only difference between SAMP and RAMP. So this compound react with the carbonyl group, and we will get this product, and this product react with LDA. LDA is act as a base. So LDA will pick out the hydrogen from this side. I have shown by a star. Then the alkylation will take place on this position. I have shown by the star, yellow star. So after the alkylation, we will remove the chiral auxiliary, that means hydrosone, and we will regenerate the carbonyl group. Okay, similarly in the RAMP also we will react with the RAMP react with carbonyl group, and after that it will react with LDA, and the alkylation will occurs in this position, and after that we will remove the hydrosone and carbonyl group is regenerated. Now next chiral auxiliary is the chiral sulfoxide. See, this is the structure of the chiral sulfoxide. Sulfur is connected to two alkyl group, and it is doubly bonded to the oxygen. There is a lone pair of electron which is in the backward direction, that is away from the observer. Now we have to concentrate on the alkylation, asymmetric alkylation of the sulfoxide. Here this is the chiral sulfoxide, and it will react with RR2 C double bond N PMP, and this is the alkylated sulfoxide. And after the sulfoxidation, alkylation, we can remove the chiral auxiliary, and the original compound is regenerated. I hope that you understood the concept of the chiral auxiliary, and what are the chiral auxiliary which are used for the alkylation. So first one, today we discussed the imine, hydrosone, and aza-enilate and chiral sulfoxide. Thank you.